All right, so we're going to do a lab about porosity and permeability, and I went ahead and added in absorption with it. So the instructions are on the first page, and then the second page is your predictions, your data table, and your conclusions. So first thing we're going to do is kind of review some materials. And so the most common things that get confused with each other is these two items. So this is a beaker and this is a graduated cylinder. And each of them has markings on them, but if we're going to measure volume of a liquid, we are going to want to use the graduated cylinder. It is more precise. This is not really meant to be used for data. It's just a guideline approximately. And so the larger the graduated cylinder is, the less precise it is. So as you get smaller and smaller in the graduated cylinders, then the more precise they become. But every graduated cylinder, you're going to have to examine it, and you're going to have to see up at the top. This one says 100 is the capacity, and then it's in 1 millimeter increments. So that kind of helps you. You don't have to really think much about it. But if that's not told to you, like for example on this one, I don't know if you can see it, but this is 10 millimeters, and so the next number that I see is an 8. So halfway between there would be 9 millimeters, and then I have 1, 2, 3, 4 marks in between, and so that means there are actually, each mark is 0.2 milliliters, and so you can always just kind of count up. So if halfway was 9, that'd be 9.2, 9.4, 9.6, 9.8, and then finally 10. So you have to figure out what they're counting by before you can actually use it. You always want to set it down on a level surface, and then you want to get down eye level and look at it so that you're making an accurate measurement. Now, when we have a graduated cylinder and it looks like this, okay, and the water itself actually bends a little bit, and this is because the air pressure is pushing down from the top, and water tends to cling, especially to glass, but plastic also, it clings. It's a polar molecule, and so we call this curve that forms a meniscus. And you're going to read at the bottom of the meniscus, okay? So you're going to get down eye level, and you're going to read at the bottom of the meniscus, and so that is how to accurately read a graduated cylinder. And I often tell my kids, you know, if you look at the bottom of it, this kind of looks like the hat that you wear for graduation, although not all of them have these, but that most of ours do, and so that kind of reminds me, oh yeah, da, 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 graduated, right? It's really not anything about that. It's because it has the markings, that's why it's graduated. But this is another piece of equipment, easy one, that's a funnel, and we're going to use that, and we're going to use it with our beaker, and then we're going to use some paper cups. I think sometimes they're called Dixie cups, I just call them paper cups, and we're going to use some water, and we're going to have some soil samples. So the very first thing that we're going to do is we're going to get 100 milliliter paper cup. I have measured it. This is exactly 100 milliliters. If I took 100 milliliters of water and filled it up, it would just almost roll over the top. So to the brim, it is 100 milliliters. The measurement on the box says it's 3 ounces, which is 90 milliliters, but that's so that, you know, you have a little bit when you hold it, it doesn't spill. It's exactly 100 milliliters. We're going to fill this to the brim with a sample. This is going to be sample 1, play sand. So on your data table, you're going to write play sand. Now, we might say it is light tan. Okay, so a little description of the sample. We're going to start out with 100 milliliters, and so when you go to fill that, you're going to take your cup. You don't want to pack it in, so you can kind of turn it to the side, let it flow in. And then when it's over the top, you're going to take, just like you would if you were cooking using flour or whatnot, you're going to flatten or scrape off the excess across the top. Okay, so now it is exactly 100 milliliters. We would say this cup is full, but we know that porosity means there is space in between all of those grains of sand. And so we're actually going to fill up our graduated cylinder with 100 milliliters of water. So then we're going to see how much space is in between each of these grains of sand by seeing how much water we can put in there. Alright, so I have filled this with water. Another piece of equipment, this is called a pipette. So you could actually, if you get eye level and you didn't quite get enough water, you could add more drops of water with a pipette, or you could take away a few drops of water with your pipette if you didn't get quite enough. Okay, so I'm starting with 100 milliliters of water, and I'm going to slowly pour and let it start to absorb or soak in. And I'm just going to keep going until it can't hold any more. Now, if it can't hold any more, we say that it is saturated, meaning it's totally unable to hold any more. Okay, so I'm going to kind of give it a little movement there. Okay, totally, it can't hold any more. All right, now, so I could have measured the mass of this before I started. Oh, by the way, I added blue to the water. It's just water with blue food coloring so that you would be able to see it. But so I could have measured the mass of this before and then measured the mass after. That's one way I could have done it. But I'm going to actually look at my graduated cylinder, and I'm going to measure how much remains. Okay, and so I'm going to get down eye level, and I'm looking at this from the bottom of the meniscus, and I am at 61 is my volume remaining, 61 milliliters. Now, if there were 61 milliliters remaining, and I started with 100, was my initial water volume, then 100 minus 61 is going to give me a pore space of 39 milliliters, because remember I started with 100. Now, I could have used another size container. I could have used 500 milliliter container. If that was the case, then I would take, this is called my pore space, so that's 39 milliliters. And I'm going to divide by the total volume of my sand, or the sample that I started with, which was 100 milliliters. And then I'm going to multiply times 100% to get the percent, rather. So 0.39 times 100, that's going to give me 39%. That's my porosity. Okay, that's the porosity. All right, so now I don't want to pour this down the drain, so I'm going to have a waste bucket where I'm going to pour off the water, and then I'll have probably a wet soil or a wet sand container where I will get rid of the sand. All right, so now I'm ready to measure the permeability and the absorption of this same sample. I'm going to get another paper cup, and this time I'm going to poke a small hole. Oop, that might be a little bit, that's too big. In fact, I've seen kids do this. That was way too big, okay? So that's not what we want, so we're going to do a different one. All right, so we just want pencil lead or a small pen, just like that, okay? Just a small hole at the bottom. Might be a little bit bigger, but about like that. All right, and then we're going to, again, get this. This is the same thing, clay sand, sample 1. And we're going to smooth it off at the top, just like we did before, just like we were baking a cake and we're using flour, right? You just smooth it off. And this time, we're actually going to hold this over a funnel, and we're going to time for 1 minute. So I'm going to actually set my, a lot of people say stopwatch, but I'm going to say timer. And I'm going to set it for 60 seconds or 1 minute. Now I'm going to have to kind of multi-purpose my hands here. I've refilled my graduated cylinder up with 100 milliliters of water, and I've colored it blue so you can see it. And so I'm going to slowly pour the liquid into the sand, and however much can pass through in 60 seconds, I'll say that's my rate of permeability. However many milliliters per minute can pass through. So I'm going to get it just about ready to pour. Let's see how good I can do this. And start. So I'm just going to pour, and hopefully it will start soaking through, it will travel through, it will permeate all the way through to the bottom. You have to kind of watch it. You don't want to overflow because you don't want it going over the sides. You just want it to be able to soak down through there. So however much I can get to go through there in 1 minute is going to be my rate of permeability. All right. Keep going. Move this, stop that, and then I'm going to put the funnel into my graduated cylinder in case any more was dripping. Okay, so I'm going to put my finger over the bottom of that so no more gets out. Okay, now I still have some water left in my graduated cylinder that did not get to go through. I also have an amount, but notice I can't measure it in here, okay? It's not even to the bottom measurement. So I'm going to get one of my smaller graduated cylinders, and I'm going to pour this amount. Whoop. Okay, well that was 10. Let's see. Okay, so there was 10. I've got another one. I'll use it. Pour this. All right, so I had 10, and now I have, let's see, that was 6, so that next one is 8, so halfway is 7. I'm going to get down eye level, so 7.2, 7.4. So 17.4 is the amount of milliliters that flowed through my sample in 1 minute. So that is my permeability. 17.4 milliliters per minute is my permeability. Now, absorption, for our purposes in lab, we're just trying to do it kind of quickly, but we would actually, if you were trying to see how much it absorbed, you might want to let it sit for an hour or so and see how much would actually soak in. But in order to figure out how much this has absorbed, I know I started with 100 milliliters, okay, and I know how much I have left. So I had 17.4 milliliters that passed through, and I have 45, 46, 47. I have 47 milliliters. So the amount that the sand absorbed was 35.6 milliliters. That's how much is still in there. And I know this because I started with 100, and this is the water that I had left. Okay? So this is what you're going to do for each sample. Now, you're going to look at all of your samples and you're going to make predictions. You're going to say, which soil sample do you think is going to